Okay, welcome to video 2.3, separate section of chapter 2. We're going to talk about how differences in the number of protons and the number of neutrons and the number of electrons, which are these three atomic particles that we just introduced, how those constitute different elements or atoms, or in other words, if we were to frame this as a question, what makes one element different from another on the basis of their subatomic particle makeup. And so what we learned is that Rutherford came in and said, well, actually the model of the atom is pretty different than what we thought. In fact, most of the density of the mass of the atom is centralized right at the core in this nucleus. And if we break out that little green dot here, that looks like this. It's a ball of protons and neutrons. Both have the same mass. Proton is positively charged, a neutron is neutral. This is a really, really, really tiny, tiny object. The rest of this space out here is made up of these really small electrons. And remember from the previous video that an electron's mass is about 10,000 times smaller than that of a proton. Or in other words, 10,000 electrons all added up together constitute the mass of a single proton, even though they have equal and opposite charges. So that has really big impacts for how these elements react. Okay, so to get to this question, what makes one atom element different from another? Really, it's about how many protons are in the nucleus. And so we call that the number of protons in the nucleus, we call that the atomic number. And so if you look at the periodic table of any one of these elements with the symbol, that number above the symbol is the number of protons that exist in the nucleus. So if we go all the way over to this part of the table, we can look at where carbon is, and we see that it has 6 protons. You can also see how the periodic table is arranged. So if we go in this direction along this row, we go from 6 to 7 to 8 to 9 to 10. And so in a row from left to right, we see the increase in atomic number, or the number of protons in the nucleus. We also call this Z. So Z is increasing as we move from left to right, and then as we get to element 10 here, neon, it starts back over, and we drop down one row, and we're at 11, 12, 13, 14, 15, etc. And so Z is also increasing as we move down the periodic table. Another way to think about this is because protons individually have mass, quite a bit more mass than, say, an electron, that means as you move over and down the periodic table, elements get heavier and heavier and bigger based on the size of the nucleus and the number of protons that constitute that. But the key takeaway here, this big message, is that the actual identity of the element is solely dependent on the number of protons in the nucleus. You can never have two different elements with the same number of protons. So proton number, or atomic number, constitutes what that element is in the first place. So the mass number is distinctly different from the atomic number, but it's also a really key and useful metric when we're thinking about the identity of different elements. So the mass number is actually the sum of the protons plus the neutrons in the atom, whereas the atomic number, or Z, is just the number of protons. And so we're adding up both of the two subatomic particles that constitute the nucleus to get the mass number. And that gives us a different type of notation that we can use, which is often not represented in the periodic table, but we can derive ourselves. So if we look at nitrogen, and we want to look at this type of notation, which allows us to assign both the atomic number, the number of protons, and the mass number, then we can look at the periodic table. We can go to nitrogen, which is right here, and we can very quickly identify that it has 7 protons. It's got an atomic number of 7. And so we would write that up with nitrogen as the symbol. We would write the number of protons, or the atomic number, down as the subscript left as 7. And then we would look at the mass number, which is the number of protons and neutrons, in the top left. And so in this case, if we know that the mass number is 14 and we know that the atomic number is 7, we can do simple subtraction. We can take the 7 protons and subtract that from the sum of protons and neutrons, and we have 14 minus 7, and that gives us 7 neutrons in this specific flavor of nitrogen. Okay, something I forgot to mention before also when we're thinking about the atomic number, which is again the number of protons, so just this part of the mass number, the number of protons of a neutral atom is also always going to be equal to the number of electrons. I'm going to write that as a lowercase e with a negative at the top. This will always be true. So if we know that nitrogen, a neutral nitrogen atom, has 7 protons, then it also means that it has 7 electrons. So 7 protons, 7 electrons, and now because we subtracted 7 from the mass number, we knew that this was 14, that's going to give us 7 neutrons. And so that, just by looking at this type of notation, we can deduce the number of all of the individual subatomic particles that constitute that particular nitrogen atom. Okay, so what happens then if we have an element that has not the same number of neutrons? So let's think about nitrogen. Again, nitrogen has to always have 7 protons. It can never have any more or less, otherwise it becomes a different element. But nitrogen can have a different number of neutrons. So an example would be nitrogen with a mass number of 15, and we would colloquially just call this nitrogen 15. So again, we could look at this and we could say, well, this has to have 7 protons, right? Because that is the identity of the nitrogen. Neutrons then is going to be 15 minus 7, which means that we have 8 of those, which is different than the 7 that we had up here. Because this is neutral, we can then state that this also has 7 electrons. And so you can see that this nitrogen atom and this nitrogen atom, they have the same number of protons, same number of electrons, but 1 extra neutron. We call these two types of examples of elements or atoms, because they're still the same type of element, they only differ by the number of number of neutrons. We call these isotopes of each other. So isotopes are 2 elements or 2 atoms that have exactly the same number of protons and electrons, but differ by their number of neutrons. Okay, another example of this, if we sort of scroll down, maybe I'll move this up here, scroll down. Another example of this would be hydrogen. So the normal hydrogen atom on the periodic table, we would write that with 1 proton, and we would write that with a mass number of 1. And so we could drop this down. We call this hydrogen. This is what we're used to. This is going to have a number of protons of 1. A number of neutrons, we'll say, is going to be 1 minus 1, gives us 0, and the number of electrons has to equal the number of protons for a neutral atom, so we'll say that's 1. We can also have hydrogen, which again has to have 1 proton, but could have a mass number of 2. In that case, protons are 1. Neutrons are going to be mass number again, 2 minus 1 gives us 1 neutron now. Electrons will still be 1. We call this deuterium. The do part coming from the 2, the mass number of 2. We can also have a third version of hydrogen where we have, again, has to have 1 neutron. In this case, a mass number of 3. So proton 1, neutron is going to be mass number of 3 minus 1 gives us 2, and the electrons are going to be the same number as protons as 1. We call this tritium. Tritium coming from the 3 of the mass number there. And so all of these 3 are different isotopes of hydrogen. they have all identical number of protons in each case, so that means they all are the same exact element, but they differ in the number of neutrons. So we have a neutron of 0, 1, and 2. And so the masses of each of these atoms are all different, right? Because a neutron actually has individual mass. Chemically, they all behave identically, which is really fascinating. And so all of these isotopes here, you wouldn't really know the difference, but they have slightly different masses from each other. So let's look at that example in what we call the heavy water demonstration. So what we have here in this glass is just regular water, but what can be added to the water is an ice cube that is made up of normal water. Normal water in this case meaning made up of hydrogen with the normal isotope with a mass number of 1. But we could also take water and freeze it where all of the hydrogens have been replaced by deuteriums, which means that it's going to be slightly heavier than that of pure water. And so I would ask you, if we were in a classroom and I was doing this demo for you, I would ask you, what would the hypothesis be? If you've got two ice cubes, one made up of normal water, one made up of deuterium or heavy water, and we drop them in a glass of normal liquid water, what would we expect to observe? So think about that for a couple seconds, and let's play this. So we're going to start by adding the normal water. Here comes the normal frozen ice cube, and it does what we'd expect. So it floats to the top. That's everything we've ever expected in life. Here comes the heavier ice cube. They look and act exactly the same, but they differ in that the mass of the hydrogens in this particular frozen water sample are heavier than that, but they look and act chemically and physically identical. So let's look at a quick additional example here using this notation that shows us both the atomic number and the mass number. So this is the element selenium, and we have it represented here. So let's think about the number of protons, the number of electrons, and the number of neutrons. So this is a good example. We should feel comfortable with identifying all of these. So we know that in this notation, this will always be the number of protons, which defines what the element is, right? So number of protons in this case is going to be 34. It's always going to be 34 as long as it's selenium. How about number of neutrons? How do we figure that out? Well, we got to take the mass number, which we have here. So this is mass number, which is the sum of protons and neutrons. And then we'll subtract the number of protons that we already know, and that's going to give us a value of 41. And then the number of electrons we know for a neutral atom, and we know this is neutral because it does not have a positive or negative charge associated with it, so it's neutral. Then the number of electrons has to equal the number of protons to make this neutral, so this is also 34 in this case. Okay, so now we know that some elements or atoms can be composed of differing number of neutrons, and we call those things isotopes. So how do we account for that in the periodic table? Because the periodic table just lists each of them once. Well, if you look at most periodic tables, not the one necessarily that I've listed here, this is a simplified version, but most of them will have each element shown in a representation that looks like this. So we've got the symbol, which tells us what the element is, which is defined by the number of protons, which is the atomic number here. In this case, carbon has 6 protons. But then it also gives us this metric called atomic weight. And this is where the periodic table accounts for the different isotopes that exist for this particular element. So remember, isotopes are atoms with the same number of protons but differ in the number of neutrons that they have. So the atomic weight tells us really the average, it's actually a weighted average of all isotope masses on Earth, just on this planet, not in the universe, but on this planet, so the weighted average of all the isotope masses on Earth for this element. So what that means is, if we were to think about carbon, if carbon had 6 protons and 6 neutrons, so if protons were 6 and neutrons were 6, we'd expect this thing to have a mass of roughly 12, because these two things are much heavier than the electrons. But what we see is, in reality, the weighted average, or the atomic weight of carbon, is actually more than that. And that's because carbon exists naturally on this planet in 3 general forms. We'll talk about the 2 primary ones here. And so when we talk about a weighted average on Earth, so again, the periodic table is useful for Earth, but not the universe. This number can actually change because the isotope ratios at which they exist on different planets depend on how old that planet or that star is. So the atomic weight, which is again the weighted average of all the isotope masses, is going to be different depending on where you look. So on Earth, what we know is that we can have carbon, which has 6 protons and a mass number of 12, which means there are 6 neutrons, just as the example we gave here. But we also have, and that's roughly 98.99% of all carbon on Earth exists in this isotope form. But we can also have this stuff called carbon-13, which again, it still has to have the same number of protons to still be called carbon, but it's got this bonus neutron, and that's roughly 1.1% of all of this. So if we wanted to think about the weighted average of these two things, really all we're doing is taking the mass of this isotope multiplied by how abundant it is, and then adding that to the mass of this isotope and multiplying that by its abundance. And so, in other words, we would take, let's say, mass of carbon 12 times its abundance in percentage plus the mass of carbon-13 times its natural abundance, which we have those 2 numbers here. So that would compute to 12 for this times, and we'll multiply this is a percentage, so we'll multiply this in non-percentage form, 0.9899, plus the mass of carbon-13, which is going to be given to us as 13.0034, times its abundance, which is 0.0111. This is going to give us this value that we actually find on the periodic table, the weighted average of all of the isotopes of carbon that exist on Earth, so 12.011. So when we're looking at periodic tables, that atomic weight is going to represent the average weight, or the weighted average, of all of the different isotopes that exist for that element on Earth. And so we'll do a couple examples of this and how we might compute that. Okay, as an example, copper has 2 naturally occurring isotopes on this planet, and I have those represented in the green text here. So we've got both obviously have to have the same number of protons, because that defines what the element is, but they differ in this copper-65 has 2 additional neutrons relative to the copper-63. Their abundances are described here, and the individual isotope masses of each one of these individual isotopes is reflected here. So what I want you to do is take a couple minutes and pause the video and try to compute what the weighted average, or in other words, the atomic mass or atomic weight of what copper should be. Okay, so what we have here, if we want to look at the atomic weight, of copper. We take the mass of the first isotope, the copper-63, times its abundance. So this would be the copper-63. We then add that to the average mass of copper-65, and what we get is 63.55 AMUs. It's important now to reflect on what we learned in Chapter 1, because this is going to carry through throughout the rest of the class in terms of the significant figures. And so in this example, we can see that we are given 4 different numerical values. Each one of these values conveniently has exactly 4 significant figures. 1, 2, 3, 4, 4, 4. So if we want to know how well do we note this answer, we need to think back through our sig fig arithmetic rules. And so we've got a couple different mixed operations here. So the first operation is multiplication, and so whatever the product of this is, this would have still 4 sig figs. We couldn't have any more than that because we never had more in the inputs to begin with. The same would be true for this case. And so we'd have 4 sig figs in each of these answers. Now we're going to do an addition operation. We're going to keep the 2 additional values beyond the decimal point, because again, in addition or subtraction operations, we're keeping digits past decimal. In this case, we'll keep 2, which allows us to have 2 past the decimal in our final answer to give us a total number of 4 sig figs in our final answer. Okay, so now that we can look at the periodic table and look at a particular element and identify its atomic weight here, or the average weight of all of its isotopes on this planet, we can start to think about this other sort of convenient unit of measure in the chemical sciences, and that's this thing called the mole. If you've taken a chemistry class before, you've learned about the mole. I'm going to talk about that in greater detail. If you remember from the very first mini lecture, the mole is actually the base SI unit for the amount of a substance. And so when we're talking about the mole, we're talking about a quantity of something. Not a mass of something, but a quantity. How many of those things? And so a mole is really analogous to a generic or an arbitrary number of things that we want to refer to. And so I often think about the mole as, say, a dozen. We all know that the word dozen implies 12 of something. We also know that the word few typically refers to 3 of something. The mole is no different. It's identifying a known quantity of something. It doesn't even have to be chemistry related. In this case, a mole refers to 6.022 times 10 to the 23rd of anything. I can have a mole of coffee mugs, I could have a mole of cars, I could have a mole of pencils, or I could have a mole of atoms or molecules. The reason we use the mole is because it's convenient to talk in these whole numbers that refer to really large numbers, right? When we talk about the number of molecules, we're often talking about trillions and trillions and trillions of them. Because they're so small, it's not that convenient for us to talk about how many. Instead, we can talk about the number of moles. It's just the same as talking about the dozens of that particular substance. Okay, so why the mole and why this number specifically, right? That's a big question. So conveniently, the mole is defined based on the atomic weight of a particular element. So the atomic weight of the element serves sort of 2 purposes. The first purpose here is that it defines the mass of one atom of that element of carbon in this unit called atomic mass units. which we've already used in this class, but I didn't define explicitly, or AMU. So if I look at the periodic table and I look at carbon and I see the atomic weight, that tells me that a single 1 carbon atom weighs exactly 12.011 atomic mass units. But how it relates to the mole is coincidentally, based on how chemists originally constructed this idea, it also means that 1 mole of carbon is equal to 12.011 grams of carbon. And so this representation here is thinking about the single atom. So when we're thinking about just the single atom at a time, we can think about it in really, really tiny atomic mass units. These are really, really small units. Or what's more often the case is we're not thinking about individual atoms. If we're working in a lab and we want to think about the actual stuff in front of us, we're not talking about a single atom, we're talking about trillions and trillions and trillions of them. We're talking about 12 grams. And so in that case, we can refer to this as the 1 mole of carbon, or 1 mole of whatever the substance is, as equal to the atomic weight in grams. That's a physical quantity that I can weigh out with tools that are accessible to a human. An atomic mass unit is purely abstract. I can't weigh that out. There's nothing that can weigh that out. But I can weigh out this. And so the convenience of the atomic weight is it gives us exactly this number, either refers to the mass of that 1 atom, or it refers to the mass in grams of a mole of that atom. And mole, the number of moles, will always be 6.022 times 10 to the 23rd of that. So if I had 6.022 times 10 to the 23rd carbon atoms, they would weigh exactly 12.011 grams. That's the key takeaway with the... Okay, so we just defined this number here, this 6.022 times 10 to the 23rd. This is the number of objects, whether it's molecules or atoms or cars or whatever, in this arbitrary sort of unit called a mole. We call that number, we also call that number Avogadro's number, which is sometimes just simplified as capital N lowercase or subscripted capital A, NA. All of these are exactly the same thing. Okay, so now that we know this relationship between this thing, a mole, which is again like a dozen, but it's not 12, it's 6.022 times 10 to the 23rd, we can answer questions like this, which is how many moles and how many atoms are in a platinum, say, wedding ring that has a mass of 9.50 grams. Okay, so how do we approach this question? Well, we need this periodic table, which I conveniently have here for you, and I need to think about what the atomic mass of platinum is, right? Because the atomic mass, as I mentioned before with the carbon example, or the atomic weight, I should say, is the weight in grams that 1 mole of that substance will weigh. So if I look at platinum down here, platinum has an atomic weight of 195.085, and that would be grams of platinum per 1 mole. So I'm going to write that like that. Okay, so this is going to require some dimensional analysis here to think about this. So I want to figure out 2 things. I want to figure out the number of moles, and I want to figure out the number of atoms. I'm going to scroll up here. I'm going to keep that in the field of view here. And let's go down here. So let's first figure out this question of number of moles. Okay, so if we want to figure out the number of moles, let's start with what we know, which is that we have a ring that weighs 9.50 grams of platinum. Okay, so let's think about this dimensionally, as we've done before. If we have 9.50 grams and we have this nice conversion factor between grams and moles, we know that for every 1 mole of platinum, it weighs 195.085 grams, right? We have much less than 195.085 grams. We only have 9.5 of it, which means that we're going to have much less than 1 mole. So we can write 195.085 grams here per 1 mole of platinum. I'm going to write grams of platinum just to keep it clear. And like we've done before, I'm going to take care of my units right off the bat. And so now if I did these operations, what units would I be left with? Well, grams are gone. All I'm left with is of moles of platinum, which is the question that I'm being asked. So if I compute this answer, I get a number that is 0.048697 moles of platinum. Okay, so let's look at this first, and let's think about significant digits. So we are given in the problem 3 sig figs in our the mass of the platinum ring, but then when we looked up on the periodic table, platinum, the atomic weight of platinum actually had 6 sig figs. Let's look at our operations here. So our operation is a division. And so we know that the division operation with sig fig rules say that we preserve the least number of sig figs in whatever the input values were. Since we had 3 sig figs here and 6 here, that means this number can't be known to any greater than 3, which means this doesn't count, this preceding 0. So we have 1, 2, and 3. So we would round up this value, and this would give us 0.0487 moles of platinum. And we'd leave it at that if this was our final answer for the number of moles, which it is to this question. We also have this other question. I'm just going to sidestep this over here so I have plenty of room, which is, well, how many atoms do we have? So if the number of atoms is also a question, what we could do is take this number that we'd just computed for the moles, and we're not going to round it yet because we want to keep all of these digits. Even though they're not significant, we don't want to round if we're going to use this number in a subsequent calculation. And that's always going to be true with significant digits. Only round to the final number of sig figs when you want your final answer. But if you want to use this number in a subsequent calculation, as we do here, then let's keep that number. Okay, so if we want to know the number of atoms, we know the relationship between moles and atoms through Avogadro's number, right? We could say 0.48697 moles of platinum, and then do this dimensionally again, where we say for every 1 mole of platinum, we have 6.022 times 10 to 23 atoms of platinum. And so we can do that math. And what we get is a number that's 2.93 times 10 to the 23rd atoms. Okay, and we'll say 2.93. I don't know what this digit is. We'll say that's a 1. In this case, we have 1, 2, 3, 4, 5 sig figs. We'll write that in blue. So there's 5 sig figs here, and we have 4 sig figs given to us in our constant. This again, this whole number here is Avogadro's number, or Na, which means that we're multiplying. We preserve the least number, which is 4. We have 4 sig figs here. So this is our final answer. This is the number of atoms. This is the number of moles. So this is really, really key to this class. We're going to do a lot of conversions and a lot of discussions with the mole. So sort of as a recap here, I want to give you a sense. The mole is useful in 2 different ways. The first way is that this atomic weight here, for any one of these elements in the periodic table, that atomic weight serves 2 purposes, right? It is the mass in atomic mass units, which is a really small, small, small number, of 1 atom of that particular element, but at the same time, it's defined as the mass in grams of 1 mole of that substance. And so it's equally useful either way, but it's almost more useful when we think about things in terms of moles, because often we're doing things on a laboratory scale. We're not measuring out 1 or 2 atoms, we're measuring out 100 grams of a substance. And so we're talking about full entire moles in that case. The mole is going to become really, really important when we conceptualize balancing reactions, because when we're balancing reactions, what we're really doing is balancing the number of those atoms that are reacting with each other. And we'll get to that in the next chapter.